We grow bacteria all the time. Well, it's got nutrients, it's got moisture, that is kind of a good idea. Give it some food and water. Proper pH of some sort, and oxygen. Now, of course, we're assuming aerobic bacteria, but that's what we use. And it's not a bad idea for it to be sterile before we start. We use agar, as you well know. Agar actually comes from algae and from seaweed, and it's actually quite commonly used in Asian foods. But we also use it, non-Asian, we also use it for ice cream and jelly. So it's used a lot for foods. Notice stable to bacteria. It's another way of saying that the agar is inert. It's inert. Nothing grows on agar. Well, of course, it does for our agar. That's because we add nutrients. We add nutrients to the agar. So really what we're using is nutrient agar. Nutrient agar.
When you're saying culture media, are you saying that's what's needed to be on the slide? Or?
No, not the slide. We're not growing bacteria on the slide. The other factor besides that nothing grows on agar unless we give nutrients is this odd thing with the boiling, not the boiling point, the melting point and the freezing point. If you remember, the two temperatures are different. So, and we've done this before. So agar melts at 100 degrees, stays liquid down at 40, and then it freezes. In 40, of course, for us it's not cold, but for agar it freezes. And then it stays solid all the way back up to 100. So again, literally the freezing point and the melting point are different. It's a very odd thing, but we can use it. The culture media can be manipulated to help identify bacteria for disease. So by manipulate, you can put other things in. So for example, selective media. This is a growth media that will suppress unwanted bacteria. So for example, brilliant green dye, and that's the name of it, brilliant green dye, will inhibit gram-positive bacteria. So if you have that in your Petri plate, or your tube, but your Petri plate, and then any bacteria that grow must be gram-negative, because gram-positive won't grow. That's the selective part, that's a selection. That the gram-negative are being selected to grow, the gram-positive being selected not to grow. That's what selection is, selective media. Is you're selecting what grows and what doesn't grow. Brilliant green dye, I say gram-negative bacteria, and anything growing is not gram-positive. The other category, differential media. Differential media. These guys make it easier to identify colonies of your desired bacteria from other colonies. In other words, it allows you to differentiate between bacteria, differentiate between different bacteria but growing on the same plate. Now, okay, that doesn't make sense. Here's an example. Blood agar. That's exactly what it sounds like. You add blood to the agar, so it's going to be red. And then that will identify Streptococcus pyogenes, because Streptococcus pyogenes can eat red blood cells. So what you're going to get after a little while is the red plate, the red agar, and clear areas. Clear areas wherever the Streptococcus pyogenes is, because they ate the blood cells. See, that would be differential media. there could very well be other bacteria on the plate. But there, it'll still be red. Now, we've actually done that. We did that in class. It wasn't blood agar. What was it? Nope. Anybody remember, what was an example? It was not blood agar. Pardon? Not yeast. Iodine, but more. What? Starch. Starch agar. The starch agar. Had to yank it out of her, but the starch agar. That's where we did add the iodine. And then if the bacteria had eaten the starch, then the plate stayed clear. But everywhere else, the iodine turned to starch dark. That was a differential plate. There were 3 different bacteria on there, but we found the one that ate starch. So that's the same thing, same kind of thing. And as you might imagine, because it is research, you can use the 2 types together in different combinations. So for example, McConkey's agar contains a combination of crystal violet and bile salts. So these inhibit gram-positive bacteria. Which means, once again, only gram-negative will grow. But the thing also contains lactose. Lactose differentiates. Again, it's all gram-negative bacteria. But the lactose will differentiate between the gram-negatives that can use lactose and the ones that don't. You'll get a lot better growth, et cetera, with the ones that can use lactose. So that would be both differential and selective. No gram-positive bacteria, only gram-negative. That's the selective part. The ones that can use lactose, that's the differential part. And like I said, it doesn't take much imagination to realize you can do all kinds of combinations to come up with different results, which is the whole point. Okay, yeah, this one, you don't need to remember this. I just kind of like stuff like this. E. coli doubles every 20 minutes, and that's actually typical for bacteria in general. 20 minutes, maybe 30, 40 minutes at the most. But 20 to 30 would be very, very typical. So if E. coli doubles every 20 minutes, in 24 hours, we'll have 10 to the 21st bacteria. So 1 followed by 21 zeros. You would outweigh the Earth. You would outweigh the Earth. Well, clearly that doesn't seem to happen. First off, we're going to run out of food. And second, bacteria have enemies just like we do. There are things that eat bacteria. So in actuality, we never take that. So why did I even tell you about it? Mostly just to show how really rapidly these guys can reproduce. Lots of bacteria. But definitely don't memorize that. That would be silly.
You're saying most bacteria though grow,
20 to 30 minutes would be extremely typical. And maybe 40 at the most.
but they don't.
Yeah, they're double. Yeah. Okay. So again, still on growth media, we have chemically defined media. Now that is when we know exactly what the composition is. We know exactly what's in there. The fact is, we usually do not know what's in there. Not exactly. Not exactly. You'll see why in a second. But to have chemically defined is actually quite rare. Organisms that require lots of growth factors, like us, temperature, pH, water, various elements, we're called fastidious. Most organisms are fastidious. Very few organisms only need 1 or 2 things. Most organisms need a whole bunch.
What is that? The chemically defined medium and exact.
Of a medium. You have your growth medium. Yeah, the agar is agar, but then what are you putting into the agar? The nutrients. You have to know exactly what you're putting in.
So you're talking about the media stuff like selective, differential.
Yeah, that could be. But see, a lot of times you're not doing that. A lot of times it's just plain growth media. You're not selecting, you're not differentiating, you're just growing bacteria.
Just to see what's growing.
But for the nutrients, again, to be chemically defined, you have to know exactly what it is. And usually you don't. Bear with me. But usually you do not know exactly what you got. That's my comment here. Usually the exact composition is not known, and here's the reason. Protein can be chopped up into unknown pieces by enzymes. What is that called? Chopped up enzyme, chopped up proteins. Peptone, that's your peptone. That's our backup food supply. You know, which we've seen now quite a bit, you know. It's your backup food supply. We've used it numerous times. But notice, chopped up into unknown pieces. You know, if you're cutting firewood, as if any of us do that, if you were cutting firewood, you don't really know how big the pieces are. You're just cutting firewood. Same thing here. The enzymes are chopping up the proteins into smaller pieces. We don't know exactly what those pieces are. We really don't care. But because we don't exactly know what each piece is, it's not chemically defined. That's why most growth media is not chemically defined. The term is complex media. Complex means that you do not know every single item. And again, the main culprit there is peptone. It's just chopped up protein. We don't know each piece. Everything else we know. I'm sorry. Oh, mystery meat? I thought that was spam. I think spam, right? But you're right, most hot dogs, it's better not to know where they came from. But yeah, that's actually a pretty good example. So mystery meat, I think spam is mystery meat, but most hot dogs would qualify, yeah. Better to eat and not ask questions. So anyhow, so most of our growth media would be complex media. Okay, a couple more things here. Sometimes yeast extracts, you kind of beat up the yeast and extract stuff out of them, have lots of vitamin B. They will be dissolved and then provided to us in the form of nutrient broth. We've used nutrient broth all quarter. So what that's been is yeast extracts liquefied.
That's the
Now,
media.
if we add agar, then that same stuff becomes nutrient agar. So the only difference between the nutrient broth and the nutrient agar is there agar or not? That's the only difference. Yeah. Why do we get the big bucks? Now, actually, that's the end of the chapter. I do have two more things to present to you.
On this chapter?
Yes. Be straight from the book, so you can read up on it easily. I don't have any more notes on them. Unfortunately, my book's a little different than yours, so my page number will be off a little. It's right at the back of the chapter, chapter 6. You don't need it now, but when you go home and stuff. Excuse me. Estimating bacterial numbers by indirect methods. Estimating bacterial numbers by indirect methods. I'm going to go get my pop hanger. My book is on page 185. In your book, it may be a little bit different, but
But it's the end of chapter.
the end of chapter 6. So estimating bacterial numbers.
Indirect method.
Yes. Okay, so quite a few of you this quarter have asked me during the course of the quarter, how did I ever get through school and do my research and everything, being as colorblind as I am? Because clearly I don't see quite a bit of stuff that you see. Well, the answer simply is that I didn't ever do this stuff when I was doing my research. I never had to use colors for obvious reasons. But what most people do, not just colorblind people, but most people, we use digital readouts. We don't need the colors. And the digital readout involves something called the turbidity method. turbidity, otherwise known as the spectral photometer. Some of you may actually have seen that one before, and maybe not. It doesn't matter actually. But the turbidity method, which means cloudiness, your nutrient broth, cloudy with bacterial growth and stuff. Now the way it works is this. You're going to have a test tube with broth in it or something else, but you start out clear. So nothing's in there except for the broth. And then the spectrophotometer has a light source, and the light shines a beam through the broth. On the other side will be a photometer of some sort, a light meter, some light-sensitive structure. Might be just a piece of film, but some light-sensing structure. So what's going to go on is it's going to measure how much light is received over here. It's going to compare it to how much light started out. Now it's all part of the same machine. So it knows how much light started. It knows how much light is coming from here. And it measures how much light comes from here. Now this thing is clear. It's got broth, but there's nothing in there. So it should all come straight through. You should get 100% reading. All the light comes through. So this would be like your standard. Yes?
But it's always a liquid.
Well, to start with. Yes, to start with. It can't be solid because then nothing will come through.
Right, you just said broth or